Our next speaker is Benjamin Metha from Uni Melbourne, and he's a geostatistician.
Hello, I am that. I'm also an astronomer, but I'm just Benji. I'm a third-year PhD student from the University of Melbourne, and I'm here to help get the most science out of your data, specifically when that data is resolved metallicity observations of galaxies. So I wanted to start with just a little bit of history of how we've understood the metallicity inside galaxies in the past. So prior to 1971, we thought that galaxies had the same metallicity everywhere. And this is because no one had ever measured more than one metallicity within the same galaxy. So because of that, Occam's razor, you just assume everything's the same everywhere. That's a perfectly good model given the data that you have. Then in 1971, Leonard Searle managed to do something incredible. By aligning split spectra in a very intelligent way, he managed to look at metallicities of multiple H2 regions within the same galaxy. And he noticed this trend that as you go away from the center of the galaxy, your metallicity decreases. This is now known as the classic metallicity gradient model. The data that informed this model looked like this. And so when you have data that looks like this, doing this is a perfectly sensible thing to do. There's more metal in the middle, less metal on the outside, fit a linear model. Over time, however, our data has gotten a little bit better. Thanks to integral field spectroscopy, which you know about now from the SAMI Hexta surveys, we can now get spectra at many individual pixels of a galaxy at the same time. And so all of a sudden, our understanding of galaxies went from this to this. With large-scale surveys like CALIPHA, SAMI, Hector, we got thousands of galaxies in the semi-local universe, depending on what that means to you, with like kiloparsec resolution. And this trend was really cemented. We did see more galaxies with more metal on the middle, less metal on the outside. But the data that we're getting now from these high-resolution IFU surveys like MUSE, Typhoon, they look like this. And all of a sudden, when you've got data this good, you can get a little bit more information out of your model. There's still that trend of more in the middle, less on the outside, but there's all of these features that we want to capture as well. And so this has inspired me to look into a new kind of models called geostatistical models that help us retain more of the information that is encoded in this data and describe it in a two-dimensional, more interesting way. So what is geostatistics and why haven't you heard of it? It's not because I invented it. I would have named it something much cooler. Instead, it was invented by this guy, Georges Mathurin. So he was a French scientist who was working in South Africa in the gold rush in the 60s, trying to understand how gold is distributed throughout a gold field. And so he did a lot of work developing this branch of mathematics called geostatistics that studies how random processes vary over a spatial domain. Now, when you think about metallicity, that is generated by a lot of stochastic processes. Star formation is stochastic, and the way that metals are mixed around by turbulence is stochastic too. And a galaxy is a spatial domain. So I wanted to use my PhD to look into if any of these techniques from geostatistics can be applied to help us better understand the metallicity distribution within these galaxies. So how does it work? Basically, the main step that we take is we break the metallicity that we observe in each pixel into multiple different components so that we can understand it in a step-by-step basis. The first thing we do is not very interesting. It's pretty common. We say that the metallicity we observe at each data point is not the true metallicity. There should also be some observational error. But if we know the properties of our telescope, which we usually do because we built them, we can understand how we expect this error to behave in a statistical way, and we can model that. We can understand what we expect that to look like. The next thing we do is something that's a bit more new. So we say that the true metallicity at each point should not just be the mean metallicity that we expect at each point, for example, for a metallicity gradient model. On top of that mean trend, there should also be these random fluctuations. So these aren't error, these are real. These are deviations from the metallicity trend caused by local features, things like recent gas infall, recent gas enrichment, turbulent mixing, things like that, that exist within our data that we want to see. So if we can model these three things, if we can see how the small scale structure, the large scale structure, and this error behaves, then we can construct better, more informative models of the metallicity distribution within these galaxies. So how do we separate the small scale features from the noise within our data? This isn't always easy to do, but luckily geostatistics has some tools that we can use to help us. And I'm going to talk about one of these tools called the semi-variogram. So a semi-variogram plots how variance between data points depends on their separation. And it's a tool that we can use to separate correlated and uncorrelated sources of noise within our galaxy. And I'm not going to go into the maths of how this works because I don't want to, Instead, I'm going to show you some pretty pictures and talk through a worked example to give you more of a sense of how this kind of behaves. So up the top here, I've got 3 different random fields. You can think of them as metallicity distributions. And underneath, I've got the semi-variograms for each of them. In this first model on the left, I have assumed that the only structure within this galaxy is just white noise, complete white noise. Nothing is correlated with anything. And so if you look at the variance between 2 nearby data points at small separation, it's exactly the same as the variance between 2 data points that are separated by a large distance. So when you plot the semi-variogram, you just get a constant, a flat line. In this next plot, I have shown a more correlated data structure. Here you can see that if you look at 2 points that are right next to each other, their variance is a lot lower than if you look at 2 data points that are further apart. And so now when you fit a semi-variogram to this, you can see how much variance there is in these small scale fluctuations and also the size of these fluctuations within your galaxy. In this third panel, I've actually done something a bit cheeky. I've just added these 2 graphs together. So now the small scale structure is still there, but because of the noise, it's a lot harder to see visually. Luckily, variance is an additive quantity. And so the variance at each separation is also an additive quantity. So if you look at the semi-variogram for these third panel, it's just the sum of the other 2 semi-variograms. Now, when you add a constant to a function, you get the same function, just moved up a bit. So using this semi-variogram technique, we can recover the properties of the small scale fluctuations within this source just as well as if there was no noise at all. Magic, right? Of course, this would never work on real data because actually here it is on real data. And it works. You can see that at small scales, all of your variance is dominated by measurement error. But as you go to larger and larger separations, you see that there is this extra variance that must be coming from these small correlated structures. And in the few galaxies that I've looked at so far with this, I find that these correlations are generally smaller than about a kiloparsec. And after about a kiloparsec, things start leveling out. Once you know this as well, you can fit a model to this and you can understand how you expect these small scale fluctuations to behave in these galaxies too. But why would you do this? What would this tell you that a metallicity gradient model can't? So one reason you might want to do this is because, when you observe galaxies with metallicities, you can only get the metallicities at H2 regions, unless you're Song Lin. I don't know how your methods work. But yeah, if you wanted to predict the metallicity at a point outside of these H2 regions, if you wanted to do it the traditional way, you'd fit a metallicity gradient. You'd say there's more metals on the middle, less metals on the outside. But when you do this, you lose a lot of the information that is within these pictures. On the other hand, if you fit a geostatistical model based on the small scale structure that you can learn from the data, you get a different picture of these galaxies. So there's still that trend. There's still more metal on the middle, less metal on the outside, but there's a lot more processes that are going on here that we can actually see. Interesting astrophysical things like these metal-enriched regions. Are they signs of recent supernova that are not well mixed into the galaxy? This thing up here, is that a recent gas pore inflow? It gives us more insight into the actual interesting astrophysical processes that are going on inside this data that we can see. These models also hold more predictive power than simple metallicity gradient models. So to test this, I took my data, I trained models using 90% of my data, excluding 10% of my H2 regions, and I compared the metallicity that would be predicted from a metallicity gradient to the metallicity that we measure at those H2 regions. A lot of words, but in the end of the day, I get graphs that look like this. So I've got the metallicity that is measured on the x-axis and the metallicity that the model predicts on the y-axis. Generally, it does pretty well, but you can see that there's a lot of regression to the mean. The metallicity of high metallicity points is underestimated, and the metallicity of low metallicity points is overestimated. And this is just because if you're assuming that everything is at the average metallicity at each radius, you're necessarily losing some of that information. On the other hand, the geostatistical model preserves a lot of that information, and so you get much more accuracy when you look at the metallicity predicted for each data point, even for these low metallicity outliers. And I've plotted on here the crosses. They're 3 sigma outliers from the model. There's the number of them that we statistically expect. So it's a really good, it seems like it's fitting the data really well. So hopefully by this point in the talk, I've convinced you that these geostatistical models are worth doing, and you're thinking, wow, this is cool. Maybe I can use this on my data. So to figure that out, one thing that's kind of like a bit of a caveat, so far I've only been testing it on really, really high resolution data, 40 parsecs per pixel. So I'm currently doing a study at the moment to see how these results change as the resolution of your galaxy changes. So what I did is I took one of these really nice data cubes from Typhoon, M82 if you're curious, M83, one better than M82, take that, Swindon. No, so I took it and I binned 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 it. And then I looked at what point do you start losing so much information that these geostatistical methods stop being useful? And early results seem to suggest that about 250 parsecs per pixel, you can still see a lot of these small scale structures and you can still tell what's going on. But generally, as a rule of thumb, I would say that if you go back, if you can still see structure in your data, a geostatistical model can probably extract that. And that's kind of like the golden rule that I'm kind of like, converging on at the moment for this kind of analysis. So this is probably useful for Duvet. This is probably useful for Mauve. And if you are interested in doing this, please come talk to me. I'm happy to talk about these methods to anyone who's interested. So to summarize, the high resolution IFU observations that we're getting from modern surveys like MUSE have an incredible amount of data that tells us a lot about astrophysical processes, especially ones that are happening on small scales, which is really important for simulations that care about sub-resolution observations, or sub-resolution physics rather. Using semi-variograms, we can separate large-scale and small-scale sources, contributions to the metallicity of the galaxy, and we can also separate small-scale sources from observational noise. And we can use these models to create better models of our galaxy's metallicity that are more informative and give better predictions. Thank you.